الآن يمكنكم المشاركة في مبادرة الأيام الرقمية تحت شعار انطلق بقوة مع جوجل، والتي يتناول فيها خبراء جوجل عناوين جديدة أسبوعيا مثل السحابيات، مهارات من جوجل، أندرويد، فلتر، ذكاء الآلة، فايربيس، ديزاين ثينكينج، مقسمة إلى دورات وورشات عمل يومية بالإضافة إلى مسابقات أسبوعية. شاهد الأيام الرقمية مباشرة على اليوتيوب وشارك رأيك وأسئلتك مع خبراء جوجل، واحصل على شهادة حضور في كل محاضرة تشترك فيها. هذا وأكثر من الأحد إلى الخميس ابتداء من الساعة 9 بتوقيت دبي عبر الرابط المبين youtube.com/gdgmena.
Okay, so we are live. السلام عليكم. Good evening everyone. Hope تكونوا بخير وبصحة جيدة إن شاء الله. So today's session, welcome in the third, I think it's the third of the first session of the series about TensorFlow and about machine learning in general with me. So I will redefine or reintroduce myself first. My name is Taha Rehah. I'm an expert machine learning trainer at Bamboo Geeks and machine learning engineer at DeepEcho. So today's session is going to be about handling imbalanced datasets, or like we're going to answer the famous question, how to handle imbalanced datasets. So this session is, to be honest, one of the most interesting like parts for me inside the EDA phase, or while doing the EDA phase. So when we say EDA, we say exploratory data analysis, which is one of the most important phases inside like building or inside the pipeline of building a robust machine learning model. So yeah, EDA phase, it's taken like a big part of building the model. And one of the problems that we can encounter while doing the EDA phase is like having an imbalanced data set or having an imbalanced classes. So in today's session, inshallah, we are going to cover how to handle this problem or this case, this particular case, and we are going to see a lot of techniques of doing this. So first of all, and before like going deep dive into how to handle this, our problem is composed with the two famous words واللي هما imbalanced and datasets. So we need to define those two words. What do they mean before? And then we are going to link them into the world of data science and into the world of machine learning to see what's going to give us and what's going to happen. So first word is dataset. So what's a dataset? It's basically a set of data or a sort of like storage, data storage. So we can say that a dataset is like a database, but in a way that we do not like read and write frequently on this database. So the dataset is a copy of the dataset. It's containing data which is static data. It's not like being there is no input or output happening on it on real time. So it was collected, then loaded and transformed, then being able like to data scientists and machine learning to use it. So basically we just like need to remember and know there is a difference between a database and a dataset. A dataset is an output from the database. The database is storing, it's just like a storage place where to store the data. But a dataset is, we can say it's a snapshot or an image of the database that's being used like with the data scientists and with machine learning engineer, and it's mostly static, not dynamic, not a dynamic or not a moving part or a moving clause. Okay, so we said, and we are going to talk about imbalanced datasets. So we defined what is a dataset. Now let's talk a little bit about what is an imbalanced, or where we do encounter that problem of imbalance or of not having classes equally or equally separated. Basically, where this problem comes to our minds or comes to our machines is when dealing with something called anomaly detection. So basically, in machine learning world, we do have a lot of problems to solve using machine learning. One of them is doing classifications. So classification is the fact of building a model that he is going to make a prediction, and those predictions or this prediction is going to not identify but classify the something. So basically, we can say that a model is classifying between a dog or a cat, or is classifying between 10 classes of fashion of clothes, or he's classifying between if that person has cancer or does not have cancer. So those problems all we can say that they are under the classifiers category or under the classification category. Inside this classification category, we do have a lot of sub problems, and one of the most famous ones is the anomaly detection, which is the fact of detecting anomaly inside the data set. What is anomaly? Anomaly is something that is not normal, that is basically not normal in our daily life or in our normal life, and we need to detect that abnormality or that anomaly. In examples, we can say that fraud detection is one of the sub problems of anomaly detection. Fraud detection is the fact of detecting fraud. We can say that we can detect if a client of a company, let's say like an gas and electricity company, wants us to build a machine learning model or deep learning model, this is being able to detect whether one of its clients is doing fraud or not. So that's fraud detection. There's also medical diagnosis. In medical diagnosis, mostly we do anomaly detection because we are just like detecting cancer or detecting anomalies, detecting diseases inside the medical images or inside medical data. So that's one of the uses of anomaly detection. There is also the spam detection, which is mostly being used by like mail providers like Gmail, like Google, the Google the service of mailing, and the most mailing providers, they do use this technique to classify whether an email that you received is spam or not. So also this is under anomaly detection. There is also anything like related to sensitive data or sensitive text can be classified under the anomaly detection. So in those particular sub problems, or in this particular sub problem of classification, which is called like anomaly detection, here where we find the imbalanced datasets. Why? Because the term anomaly is by its definition, it's something that is rare, or it is something that is imbalanced, because as we all know that we are humans, and by definition we humans have the tendency to not find anomalies more frequently in our world. So basically, persons that do fraud are much less than persons that do not do fraud, and also persons that have cancer, that were diagnosed with cancer, are very much less than the persons that has cancer. So anomaly, it's by its definition, it's in nature, it's imbalanced. We cannot find something that is an anomaly, and that anomaly is bigger, or it's much higher than the normal thing. So this is a normal problem, and a very common one in our daily lives, and we need to handle it, because we cannot stop here and say, yeah, it's normal, and we move ahead. No, because our models and our machine learning workflow is going to be biased, as we say in Arabic, enhiyas. So basically, our models are going to be biased to the normal classes or to the normal thing, and they are not going to be able to detect the anomalies. They are going to be able to detect the normal things, but not the abnormal things, or not the not normal things. So that's the problem, and that's why there are some techniques to handle this and to make this not a big problem, and we can overcome it and go over it in a simple way. So let's see how. Yeah, next slide. Okay, so basically this is an example of a distribution of fraud. So I took a data set, an example of the data set, and I plotted two classes. So the data set is basically about detecting whether a person or whether a client or I don't know what is doing fraud or not. So I plotted the two classes, the numbers that are in the two classes, and basically we found that and we have 127,000 of persons that are not fraud and only 7,500 that they are doing fraud. So there is a huge difference and there is a huge imbalance in this data set because persons that are not doing fraud are like much higher than persons that are doing fraud, and this is what we were talking about just before, and we said I know it's normal, like it's normal that persons or that people that are doing fraud are not like more frequently to do it. So we need to see how to handle this. The first problem that we are going to encounter if we go over this imbalanced dataset and we train our model on this imbalanced dataset, just like this, just with those numbers without doing any pre-processing or without doing any imbalanced dataset handling techniques, we are going to find something like this. We are going to have like this is a chart showing us that different models, different classifiers, decision tree, ADA boost, gradient boosting, random forest, light gradient boosting algorithms, etc. And it's showing us the accuracy of those models if they were trained with the dataset without handling the imbalance on it. So you can see, and we have 100% accuracy with decision tree, 100% with the ridge classifier, 100% with the ADA boost, etc. So we have big numbers. The most or the minimum accuracy that we have is it's 83%, which is something good. It's still something good, and it's still something not bad. So if we did this and we have those metrics, everyone or most of us we are going to say, oh, we have 100% accuracy. It's good. Why would you need to handle imbalanced datasets? It's normal. We are looking to making the accuracy something bigger, so we are looking to increase the accuracy everywhere. And now we have 100%. So maridna ma عنده بس, as we say, and it's done. Actually, it's wrong. This is 100% wrong, and this is totally wrong, because the accuracy it's making us confused, and this is just an illusion of numbers. But basically, we need to look into something else to see that we are wrong, and to prove ourselves that we are wrong and that we are not on the right path. So the first thing that we need to take care of and to look about is the metrics. Basically, the accuracy is not the right metric for us here in the case of imbalanced datasets. Never look into accuracy when you have an imbalanced dataset. Like accuracy, yes, it's something that we need to take care about, but not the most. It's not the most important thing. There are other metrics like the precision, the recall, the F1 score that we are going to see what do they mean shortly. Those metrics are the ones that are going to show us if the model is good or not. If we only look to the accuracy is not accurate. It's the opposite of its name. It's not accurate when the case of imbalanced datasets. We need to take care, or we need to take attention of this and like look into other metrics that we are going to see right now. So the first technique, this is the first technique, and this is the first way how to handle imbalanced datasets is to look into metrics, the right metrics, and not go with the illusion of accuracy and with the confusion of accuracy. So in order to understand metrics and in order to understand what's happening or how those metrics are being are showing us that we are wrong, we need to understand something called the confusion matrix. The confusion matrix, which is a concept that I do beg that every one of you have heard about, if at least you had a small experience with machine learning and with data science in general. The confusion matrix is just a simple table, a simple matrix that it contains in its vertical rows, in vertical column, the predictions that the model has made, and in the horizontal rows, it contains the original label or the original response. So basically, there are two things. There is basically in our data set, we do have the point or the data and its label. What we call label, it's the ticket that is telling us what is the type or what is the class of the data. So basically, if you want to detect fraud and not fraud, our data set contains rows of people that are doing fraud and not fraud, and there is a column which is called the target column or the label column. It contains the tickets that is telling us if this client is fraud or not, and we are going to train the model based on this, and then on the predictions we are going to make it just like do predictions, and we are going to verify whether the predictions are true or not, because we already have the response. So we did give the model some data. It's just like an exam. The professor, which is like the data scientist, has the exam and also has its responses, or has the response of the questions. So he gave to the students, when your students in this case, Homal model, or the students here are the model, our model. They are going to take the exam to pass the exam, and the professor is going to correct for the students, correct the questions, and he has the answers, he knows the answers. So basically it's the same thing. The predictions are the answers of the students, so the predictions are the answers of the students, and the original are the responses that like the professor or that the teacher has on its own. So if you understand very well this, you are going to understand what is a confusion matrix easily. So remember, we have the predictions. The predictions are the responses that the model is doing. So it's the output of the model. And the original classes, Homal classes, or the tickets originally put in the on the data or on the data set. So the confusion matrix is showing us the relation between the prediction and the original in two ways, called positive and negative. So there are four variables here, homa true positives. True positive are the predictions that are positive and they were originally positive. So those are true positive, and those are good. Those are good. There is also the true negative. True negatives, homa or true negatives are the negative predictions. The model predicted that they are negative, and they are actually negative. So they are true. Those are called true negatives. There is also two other variables اللي هما false positive and false negative. So basically a false negative is a prediction that the model has made that it's negative, but it's actually positive. That's called false negative. And for false positive, it's completely the opposite of false negative, which are like the predictions that made the model. The model said that X is positive, but actually X is negative. So that's false positive. It's the same thing for the others. If we take an example of classifying between happy and unhappy, and we took a person X, that this person X, we know that he is happy, and the model predicted that he is unhappy. So this is false negative. If it's the opposite, if the model predicted that he is happy, but he is actually unhappy, this is called false positive. And true positive and true negative are simple. If they are happy, the model predicted they are happy. This is true positive. If they are unhappy and the model predicted that they are unhappy also, this is true negative. So this is what is a confusion matrix, and it's important to understand what is this all about, and what's like the confusion matrix is showing us. Okay, now let's talk about how to calculate, or how those metrics are being calculated. So there is the confusion matrix. We understand the confusion matrix, and I said that the accuracy is a bad bad, or it's a bad that you do not need to take into consideration. It's a metric that you don't need to take into consideration. Why? Because it's being calculated out of the sum of true positives and true negatives, out of the sum of all the predictions. So basically, what is the accuracy? The accuracy is how many true and how many correct predictions that I made out of all the predictions that I made. This is the accuracy. This is how the accuracy is being calculated. So what is accuracy? Accuracy والا الدقه هي مجموع البريدكشنز، مجموع البريدكشنز الصحاح الكوريكت بريدكشنز اوت اوف مقسومه على المجموع البريدكشنز الكل اللي عملتهم out of like all the predictions of the whole predictions that I made. So this is the accuracy. This is wrong. Why? Because this is only taken into consideration true positives and true negatives. It's not taken into consideration the false positive and the false negative. And we said, and no, we have an imbalanced data set, which means, and no, which means that like we have two not equal classes. This is bad, and we need to take into consideration the false positive and the false negative. Those are two important variables that we need to take into consideration. And if we are using only accuracy, we are negliging, or we are ignoring those two variables, and we need to take them into consideration using other metrics اللي هما. The first metric that we are going to talk about, it's precision. Precision. Basically, precision is answering the question of how many positive predictions were actually correct. So what is precision? We said, and no, accuracy is how many correct predictions out of all the predictions. But the precision is how many positive predictions are actually correct. So please concentrate with this. Prediction or accuracy. Accuracy is how many predictions are correct out of all the predictions. The precision is how many positive predictions are actually correct out of all the positive predictions. So the precision is true positive. We take the true positives out of the sum of all the positive predictions that I made. I only take the positive predictions, like here. I only take this column, and I take the true positive, and I calculate the percentage or the rate of the true positives out of the sum of all positive predictions. This is what's called precision. Where like we do need to use precision. Basically, we do use precision when there is a high cost of false positives. Or what's called high cost of what is a high cost of false positives is where like where we have a problem that the false positives does matter a lot, does matter more than the false negatives. Let's take an example. For instance, مثلا, we have Gmail, and Gmail is doing spam detection. So he's like receiving emails. You are receiving emails on your email folders, and Gmail is responsible of like classifying the emails into spam and not spam. Let's assume that you received an email, and no, he's not spam, but actually Gmail was detecting that it's spam. So the actual email for real, he's not spam, but Gmail said that it's spam. This is what's called false positive, because it's the model or the Gmail predicted that it's positive for spam, but actually it's negative. So this is false positive. And this is going to cause big or it's maybe cause the company some losing some good informations. Maybe this email has containing an offer or has containing something like related to business. So that's why it's bad, and the cost of false positive is high. And in this case, we do use precision when we have a similar case of this. Sorry, we do use precision to handle this. So that was the first metric. We talked about accuracy. We talked also about precision. Now let's talk about the third metric, اللي هو recall, which is like recall. Recall is answering the question of how many actual positives were actually identified correctly. So let's go roll back a little bit, Dima, to make it clear, to make the image clear. We talked about accuracy. Accuracy, which is the total predictions, the total correct predictions out of all the predictions. The precision is how many correct positive predictions I made. The precision, the recall, is how many actual positive that are correct. How many positive predictions are correct. So this is what's recall, and the difference, like to see the difference, like just see here and know. For recall, I'm taking how many positive predictions I made out of all the predictions, not all the predictions, but out of all the positive predictions that I made. Positive, homa, true positive, or false negative. Instead, in the precision, I took the true positive out of true positive and false positive, only false positive and true positive. But in recall, I'm taking the true positive and the false negative. So I'm asking the confusion matrix to give me how many actual positive are correct, how many actual positives that I have, and they were identified correctly by the model. This is recall, and when we do use recall, basically the opposite of precision. So precision, we said that it's being used when there is a high cost of false negatives, or false positives, and the recall is being used when there is a high cost of false negatives. Let's take example مثلا كيما خدينا السبام. Yeah, let's say that we want to build a model that is detecting cancer, لا قدر الله, cancer inside like out of the medical images or out of brain images, just for instance. So the model, let's assume, and the model predicted for person X that he does not have cancer, so he was diagnosed with no cancer, but actually person X has cancer. So this is false negative, and this is dangerous for the person X. Why? Because the person X is going to go and live like a normal life, but actually person X has cancer, and like one day it maybe got complicated, and maybe it's too late to like take it into consideration by medical teams, and this is going to be bad. This is going to be bad for person X. So there is a high cost, and this is not allowed to the model to do it. So the model is not allowed to predict to have a high false negatives rate. It's not allowed to do a lot of false negatives. That's also that's where we do use recall, and that's where we do need recall. Okay, so that was the third metric, or the third metric. Now let's talk about the fourth one, اللي هو F1 score. F1 score is just like a combination between precision and recall. Just like simply, if you have a case of a problem that there is no need, like there is no high cost of false positive, and there is also no cost for for false negatives, then you are going to take a combination between both. So either there is no high cost for both, either there is a high cost for both. So in this case, you are going to need a combination between the recall and the precision, and this is what's called F1 score. F1 score is just like 2 times the precision times recall divided by precision plus recall. This is F1 score. There is nothing special about it. It's just like, as I said, the combination between precision and recall. Now let's talk about another metric. اللي هو also it's so much interesting actually, more than the precision and recall, and it's being used widely in imbalanced datasets. So like before even talking about it, just want you to make that mind connection on your mind, like just like make the connection between those metrics and imbalanced datasets. So we have imbalanced datasets. Imbalanced datasets is having like two different, not equally classes. Okay, if the model has not equal classes and we use it accuracy is going to be high. Why? Because most the predictions that I made are true because they are not normal and because I have big classes of not normal of normal sorry of big classes of normal cases. But actually I have few classes of anomalies and the model is not making good predictions on them, but because they are small, the accuracy is not taking them into consideration, and I will have a good accuracy and a high accuracy. But instead, maybe I have like high false positives or high false negatives, which is something not good and bad, and they need to solve it. So in order to detect this, I will use those metrics. I will use precision. I will use recall, and I will use something called ROC or AUC. What is ROC? ROC is the receiver operating characteristics, and AUC is the area under the curve. So basically, ROC is just a curve that has in its x-axis of FPR, a false positive rate, and it has on its y-axis stands for true positive rate. So what is this curve and why we do even need this curve? Basically, this curve is showing us the progress of the rate between positives and negatives between two classes. How the two classes are being handled, or how the model is going to define or is going to determine whether it's class A or class B. Like the how to interpret the ROC. If the ROC is close to 45 degree, if the ROC is close to this line, then it's bad, and if it's far to this line, it's good. So this is the only criteria that you need to take into consideration. Okay, so what is TPR and what is FPR? TPR, or recall or sensitivity, it's TPR, it's simply equally to recall, so it's true positive out of true positive plus false negative. This is TPR, or also this is recall. Then there is the FPR, which is 1 minus the spec, or 1 minus the specificity, which is true negative out of true negative plus false positive, which is a formula. And the FPR is 1 minus that spec. Okay, so we have in the x-axis, let me go back here. In the x-axis we have the FPR, and in the y-axis we have the TPR, or the true positive rate. Okay, that was the ROC. And for the AUC, how to interpret the AUC? AUC is the area under the curve, or the area under the ROC. So basically, it's just an mathematical integral, or as we all have seen in high school, how to calculate areas under some curves. It's the same thing, and it's the same definition. But just like how to interpret it is when we do have AUC equals 0, it means that the model is making opposite predictions, which means that if the AUC equals 0, it means that the model is, when the class is 1, the model is prediction as 0, and when the class is 0, the model is prediction it as 1. So the model is making like opposite predictions, or making different completely opposite predictions. This is AUC. When AUC equals 0, you can see here that the true negatives and the true positives, basically the true negatives mean the green curve needs to be on the right and the red curve needs to be on the left, but they are switched because the AUC equals 0. And also when the AUC equal 1, which is the case here, the AUC equal 1, which means like that the model is perfect, that the model is making predictions, true negatives as true negatives, negatives as negatives, and positives as negatives, as positives, which is good. And this is the case where AUC equal 1, واللي هي تشوفوها on the screen. now like when the accuracy, when the AUC decreases, when the AUC is going to decrease and it's going to be like close to 0.5 or to 0.5, it means that the model has no capability to predict. Which means like the model, if you give it an input, he's not able to predict if it's 1 or it's 2, then he's going to predict other. So there is a class called other. We can define that there is a class called other. And when the model, he cannot predict if it's 1 or 2, he's going to tell us that it's other. And yeah, that's it. So if the AUC is 0.5 or it's close to 0.5, this is what it means. And this is the correspondent curve to it. Then there is when the model equals 0, when we talked like in the first case, the model equals 0, which means that this is the case when the AUC equals 0.5 exactly, which is like rarely to find this. So it's rare to find the AUC equals 0.5 exactly. So, but when you find it, it means that there is no capability for the model to predict if it's class 1 or it's class 2. Then there is like the AUC. When the AUC equals 0, completely 0, we said no, it's the opposite. So you can see no true positives are here and true positives are there. So they are switched, and this is bad, and this is bad and good. It can be interpreted, to be honest, in the opposite way. So it's if AUC equals 0 100%, then you can switch between the interpretations. But you will never find an AUC equals 0. It's rare to find an AUC equals 0. But if in case you found it, subhanallah, you can like say that 0 equal 1 and 1 equal 0, like the opposite. You can do the opposites on your own. Yeah. Okay, so basically the first technique or the first thing to take into consideration when you have an imbalanced dataset was the metrics. So is there any question about the metrics before switching to the other technique, which is resampling, that contain two main techniques, اللي هما oversampling and undersampling. But before going deep dive on it, is there any question about the metrics? Let me check the chat. Okay. Okay, so I think basically it's clear for the metrics. Okay, so let's move on to the other technique that you need to take. Okay, so I have Mohammed and Usama here. Okay, great. So if it's clear, let's move out to resampling, to how to do to the other technique that comes after the metrics, واللي هي resampling technique. So as I said, there are two main techniques on resampling, which are oversampling and undersampling. To be able to understand very well those two concepts, let's go back a little bit and remember our problem. Our problem is that we have a difference between datasets, between classes of a dataset. Okay, so we have a class, maybe class 1 it's higher than class 0, or maybe class 0 it's higher than class 1. So it's either 1 or 2. Undersampling is getting down the biggest dataset to be equal to the minority dataset. So if I have a majority dataset اللي فيها an example that contains an example 1000 class 1000 row, and I have a minority class that only contains 100. So undersampling is making the 1000 class equal to 100. So in this way I will have two equal classes. Each one contains 100, 100, and they are equal. So there is no imbalance here. Okay, so this is the first case, which is called undersampling. I'm going to undersample. And the opposite is oversampling. Oversampling is when I'm going to get the minority to be equal to the majority. So if I have, as I said, the same example, a class that's containing 1000, and the other class is containing 100. So oversampling is making or taken out from the minority from that 100 to be equal to 1000. So in this way, I'm oversampling the minority class to be equal to the majority class. This is oversampling. It's simple. It's basically a simple concept. So undersampling is getting the majority equal to the minority. Oversampling is getting the minority equal to the majority. Okay, so hope it's clear and hope it's simple. So how to do this? Basically, there are two ways. Either we do it randomly, or either we do it in using a specific function or using a specific technique. If we're going to use it randomly for undersampling, I'm just like going to delete some samples to be equal to the minority class. So this is random undersampling, and it's same for random oversampling. Random oversampling, it happens with it happens like just like with copying or duplicating the minority class. So let's stick with the example that has class 1 contains 1000 and class 2 contains 100. Random oversampling, which means that those 100s, I'm going to duplicate them 10 times so that they are going to be equal to 1000. So this is random oversampling. This is, you can constate and you can observe that this is bad because I'm just duplicating values, and maybe duplicating values is going to be confusing for the model, or maybe it can take it to another path or to another side. So it's bad. Random oversampling, yeah, it's still good, or it's still good to use it on some cases, but you can understand that it's not going to be useful a lot for the model. It's same thing for random undersampling, because I'm deleting rows, I'm deleting points of data, and when deleting, always deleting something is crucial. Always the delete operation is crucial. So if I'm doing random undersampling, I may lose some critical informations or some good informations that they may be that maybe those data points, those deleted data points, have been holding over. So yeah, this was the random techniques. Now let's talk a little bit about the actual techniques that are like following some algorithms and some logical workflow. The first technique, it's called SMOT. SMOT stands for Synthetic Minority Oversampling Technique. So you can constate, or you can observe from its name, that it's an oversampling technique. So it's going to take the minority to the majority. So this is oversampling. How it's being done? It's being done by generating a synthetic points or synthetic data using the KNN algorithm, or using the key nearest neighbor algorithm, or algorithms like this. So it's going to generate new data points that are not being existing in the data, and they are synthetically generated by the SMOT technique. And this can be useful because like doing data augmentation in deep learning and in images, it's the same concept. So I'm generating new data, and I'm making the model making like this to the model more useful to the model, so that it can train and it can generate better results. So I have a question here: can oversampling bias data? Actually, the data is already biased. We can say that we can say a little bit that it's already biased because it's imbalanced, but it's normal bias, it's implicit bias. And when doing oversampling, actually I'm not biasing. No, I'm making the two classes equal to each other, but I'm duplicating. I'm just like duplicating the values. So it's not going to be useful, Saraha, to be honest, to the model. I'm not biasing it, but I'm just like duplicating, and it's going to be like just like doing no there is no additional feature to the model. Okay, another question. Can we use it with imbalanced textual data? The SMOT, if you are referring to the SMOT technique, yes, it can be used with imbalanced textual data. But basically, I never like tried it with textual data. I mostly like tried it with numerical and categorical like data. But if you are referring to textual, you are referring to NLP, or you are referring to texts and speeches. it may not work very well. There are other techniques of data augmentation. Yeah, you mean SMOT? Yes. If you mean SMOT, use it combined with texts like handwritten or texts generated from web scraping, etc. It may not very work very well because generating text is not simple as generating numbers or generating categorical classes. So generating text is something complex and it's a whole field of its own. So I do not think that SMOT is going to work. But there are other data augmentation techniques that can be applied to NLP. Inshallah, we are going to have a session about them, about NLP and about data augmentation techniques in computer vision and NLP. Okay, so let's move to the other technique, which is tomic links. So the SMOT was for oversampling. The tomic links is for undersampling. So tomic links is a method made by Tomic that is going to just like delete delete some values or delete some points from from our data sets, so that it's undersample, but it's not randomly deleting. It's not, no, it's not. It's just going to go and look for data points that are close to the other class. مثلا we have class 1 and class 2. It's going to go and look for points from class 2 that are very close to class 1, and it's going to delete them, to delete those class 2 points. This is undersampling technique, and it's going to be useful. Why? Because it's basically not randomly deleting, but deleting based on something and based on a technique called clustering in machine learning. Okay, so for reviewing this, we talked about metrics. We talked about oversampling, undersampling. For oversampling and undersampling, we have two main methods. The first one is randomly oversampling and randomly undersampling. Then there is the SMOT technique for oversampling and the tomic links for undersampling. Okay, so those are basically the techniques to handle imbalanced datasets. Those are the specific ones. And basically, here we come to the third technique. Well, it's simple, just like to go and penalize your algorithm. So what is penalized in your algorithm is to make the loss higher. And when the model is doing a bad prediction, a false prediction, either it's false positive or either it's false negative, then you are going to penalize it a big penalty to over this. So if the model made a false prediction, then you are going to tell them that this is bad, and they are going to make the loss higher. So the model is going to go and retrain and understand the data, so that like he is going to avoid doing false positive or avoid doing false negative. This is also one of the most well-known techniques. Then you can just like simply change your algorithm. You can just like if you are using random forest, you can go ahead and use decision tree, or you can go ahead and use gradient boosted algorithms like XGBoost and etc. So also changing the algorithm may come to help when handling imbalanced data sets. So yeah, we have like talked about four techniques, basically four techniques اللي هما الماتريكس, undersampling and oversampling, penalizing the algorithm, and changing the algorithm. Basically, those four techniques are the most famous ones and the most used ones in the world of data science and machine learning. Specifically machine learning. We did not mention deep learning here because it's a whole other world of handling imbalanced data sets. But in machine learning, basically those are the four techniques, and those are the four things that you need to take into consideration. And with experience and with practicing, you are going to develop the intuition in your mind, so that like all those techniques are going to be easy for you and good for and make your results and predictions good. So with this, we have reached the end of today's session. If you have any question, please we'll wait for a couple minutes. We still have a couple of minutes. If you have any question, please do not hesitate to type them on the chat. or if we are offline, you can just contact me on Twitter using the tag Taha Rehah, or you can email me on taha@bambogeeks.com. Is there any question, or is everything clear? Okay, so we have a question. How to measure the quality of undersampling and oversampling? Good question, Mohammed. Yeah. Actually, if you are talking about the quality of the measurements, you are referring to basically to referring how we can measure the quality. We only can measure it by the quality of the predictions. So the quality of oversampling and undersampling, we know if oversampling and undersampling was good and was successful, just like by knowing if the predictions or if the precision or recall, depending on your case, are good. So if you made oversampling and the precision is low, then you tried undersampling, then the precision is higher, then the quality of precision of undersampling is higher than the quality of oversampling. And if you are also wondering when to choose oversampling and when to choose undersampling, it depends on the case of your data. So basically, مثلا, or an example, you cannot do oversampling for invoices or for invoices of clients, but you can do undersampling. It's easier to do than oversampling. So in some other cases, it may be the opposite. So there is no this or this. And for the quality, for answering your question about the quality, as I said, the quality is dependent on the quality of the prediction. So you cannot know whether the undersampling or the oversampling was successful, just like by only by knowing the predictions, how the model is performing when given it an oversampling or an oversampled or undersampled data. So the quality of the EDA depends on the quality of the prediction. I hope I was clear, Mohammed. Any other questions, guys? You are welcome, Mohammed. So if no other question, I will say Assalamu alaikum. Thank you for attending this session. We'll see you inshallah in another session, another topic, always about machine learning and always about data science. So thank you. Assalamu alaikum.